Hi everyone, welcome back to another webinar. Hope everyone had a nice evening. Today we're going to be covering nuclear physics. It won't be the entirety of nuclear physics because it's a huge topic, but I'm going to cover some of the bits that I think are the most complicated and try to clear those up for you. And then after we've been through the content, we're going to look at questions from all three of the webinars this week. So there'll be electricity questions, there'll be electromagnetism questions, and there'll be nuclear questions as well. There'll be a mixture of hard and some easy ones, but yeah, we'll go through those together and do some work solutions. As always, feel free to put questions in the Q&A box and the answers to the questions that I ask in the chat box. That will really help me out so I can see all the questions nice and clearly. Cool. I think we'll get started. So these are the answers from yesterday's questions. Just for the recording, you can pause the video and check, although we will be going through some of them today. Okay, so the AQA syllabus, as always, we'll go through it, see what you need to know. Okay, so there's three topics: atoms and nuclear radiation, hazards and uses of radioactive emissions and of background radiation, and nuclear fission and fusion. Those in bold are the ones that we're going to be covering today. And they're probably some of the most complicated. Okay, so radioactive decay, I'm sure most of you will have heard of before. Radioactive decay it's a really weird concept because it's really, really random. Scientists have come up with lots of theory around it, lots of experiments and lots of analysis around it, but it's still a really random nature of radioactive decay, which means that we only have certain ideas about it, and there are still a lot of things that we don't know. But why does radioactive decay happen? Why does this really random thing happen? That we do know. So radioactive decay happens because unstable things want to become stable. Okay, it's the natural desire of an unstable nuclei to want to become stable. That's the reason that radioactive decay exists. So some nuclei are unstable. You don't need to know why they're unstable, you just need to know that they are unstable. And they want to become stable, right? So the way that they do this is they emit alpha, beta, or gamma in order to become stable. Okay, so by emitting one of those three things, they are able to become stable. That is what's known as radioactive decay. Giving out alpha, beta, gamma is known as radioactive decay. Activity is this key term that we use to measure the rate of radioactive decay. So how many decays are happening per second? Is it really radioactive? Is it giving out a lot of decays per second? Or is it not so radioactive? It has a low activity. It gives off small amounts of decays per second. The way that we measure that is in becquerels. Okay, becquerels, which is BQ. That's the unit for activity. And then we can also measure count rate. Okay, so count rate is the number of counts that a Geiger-Müller tube will pick up every second. Maybe you've seen a Geiger-Müller tube before, maybe you haven't. It's literally a black tube, and when you put it near a radioactive substance, it measures the rate of the number of counts. Okay, so how radioactive a substance is. Activity and count rate are two very, very separate things. Activity is the number of decays per second, and count rate is the number of counts on the Geiger-Müller tube. Okay, so they become stable in one of four ways. In key stage 2, 3, you probably heard of alpha, beta, and gamma. Year 7, 8, 9, you probably were only thinking about alpha, beta, and gamma. But there's actually one more that a lot of people tend to leave out, but it is just as important, and it is still another way to become stable. Okay, so the unstable nuclei is going to pick one of these 4 ways, or maybe a combination. It might do 2, that's fine, in order to become stable. Okay, alpha, beta, and gamma, and neutron. So let's talk about the nature of these radioactive decays. Alpha consists of 2 protons and 2 neutrons. Okay, so it's really, really simple. It's just 2 protons and 2 neutrons, and that is all alpha is. It does not include electrons. Okay, that's super important to understand. It does not include electrons. Okay, now I'm sure you guys have seen lots and lots of pictures of what an atom looks like, and it looks exactly like this diagram on the left here. This diagram here. So what I've put here is a helium atom. Okay, a helium atom. But the bit that's circled in pink is the helium nucleus. Okay, so remember, the nucleus is the bit where the protons and neutrons are. The atom is also including the electrons, but we don't care about the electrons. They are not part of alpha. Okay, alpha is just this center part, this helium nucleus. So alpha is also known as the helium nucleus, the nucleus of the helium, the bit where there are 2 protons and 2 neutrons. Okay, beta is a neutron in the atom, in the unstable atom, that wants to become a proton. Okay, the neutron wants to become a proton because protons are really stable. Protons are the most stable thing ever. So the neutron wants to turn into the proton because he wants to be stable, right? But in order for the neutron to turn into a proton, it has to lose an electron. That is the cost of him becoming stable, basically. And that electron that is lost is known as beta decay. Okay, so it's not enough to just say that beta decay is just an electron being emitted. No, it has to be a proton turning into a neutron, and in the process of doing so, it loses an electron. Okay. Gamma is electromagnetic radiation. If you've covered that, then you'll know exactly what gamma rays are. If you haven't, you will get to it, and it's part of the electromagnetic spectrum of waves, which looks like this picture here. So it starts with radio waves and it goes all the way up to gamma rays, which is circled in pink. So gamma radiation is just those gamma rays from the electromagnetic spectrum. Okay, and then finally, the neutron. A neutron is emitted in nuclear fission, or it can be randomly, or we can force it to be emitted. Any way that it happens, if a neutron is emitted, then it becomes more stable, and that's another way of radioactive decay. Does anybody have any questions about any of those 4 ways in which it can become stable? Let's have a look. So alpha is just helium. Yes, alpha is just the helium nucleus, not helium, the helium nucleus, only the middle part of helium, okay? Not going to get the marks if you say that alpha is helium, because it isn't. It's only the center part, the nucleus of the helium. It goes from a neutron to a proton. As it says, a neutron wants to turn into a proton to become stable. But in order for the neutron To do this, it has to lose an electron. So does that mean when gamma radiation happens, the element stays the same? Yes, absolutely. Gamma is just a wave. It's just radiation. It doesn't change anything about the nucleus. It is just radiation. It's just bits of energy. Isn't the neutron the stable one? No, neutrons are not stable. Protons are the stable ones. This is all normal tier stuff, not higher tier. Still part of AQA. This is the topic that involves half-lives, and no, it's not part of electricity. Okay, I think I've answered all the questions. Let's move on. So we need to know about the nature of these types of radioactive decay. So we've got alpha, beta, and gamma. They're the three main ones. And their symbols. So these are what the symbols look like. A little fish symbol, if you like, a B with an extra long tail, and the gamma kind of looks like a Y. And you might need to know this. So they might ask you that in the exam. Okay, so penetrating power. We often compare and contrast alpha, beta, and gamma in terms of their penetrating power and their ionizing power. Penetrating power means what can they get through? What can they penetrate? What materials can they actually get through? Okay, and what stops them? So for alpha, a simple piece of paper, or by you putting your hand in front of it, is going to stop alpha. Alpha will not get through your hand. A sheet of paper, anything that's kind of along those lines, something thin, right? It only takes a piece of paper to stop alpha, which means it's not very penetrating and can't get through very many materials. Beta can be stopped by 3 millimeters of aluminium foil at minimum. Okay, so if we put 3 millimeters of aluminium foil in front of a beta source, then that's going to stop the beta from getting through. Then gamma. Gamma is going to be stopped by a big piece of lead or concrete. So it's very, very penetrating, and it must be stopped by this big block of lead. It's not going to be stopped by paper. It's not going to be stopped by foil. So you might want to have a look at this diagram to make a bit more sense. As you can see, alpha gets blocked by the hand, beta gets blocked by the foil, and gamma can go through the hand and the foil, but it will be stopped by a big piece of lead. Okay, so therefore gamma is the most penetrating and alpha is the least penetrating. Then we talk about ionizing power. Now, ionizing power is a tricky concept. Ionizing power refers to an atom being ionized. So to ionize is to change an uncharged atom into a charged atom by adding or removing electrons. So ionizing power is basically how good is it at knocking out or adding electrons. Okay, so when it hits this source, how good is it at removing the electrons from the source? That's what ionizing power means. Okay, so to change something into an ion is to remove or to add electrons. To ionize is to remove or to add electrons. So if it has a high ionizing power, it's really good at adding or removing electrons. If it has a very low ionizing power, like gamma does, it's not very good at ionizing. It's not very good at adding or removing electrons. Then we can also talk about their range in air. So alpha, it doesn't have a very long range in air. It can't really exist for any longer than 5 centimeters in air. Beta can go undisturbed for 1 meter, and gamma can go undisturbed for much more than 1 kilometer. Okay, so that's if nothing's blocking it, how far can it get? So if nothing's blocking alpha, it's only going to get that far. If nothing's blocking beta, it'll get about 1 meter. And if nothing's blocking gamma, then it can go for kilometers. Okay, so that's how long it lasts in air if there's nothing disturbing it, of course. If something disturbs it, then it's obviously not going to last. Okay. Does alpha and beta change the element? Yes, alpha and beta changes the element. Gamma doesn't. Ionizing things is dangerous. Yes, good. If we knock out an electron, if we add an electron, it becomes a charged particle, and charged particles are dangerous. Can gamma radiation kill humans? Yeah, gamma radiation can kill humans. All radiation can kill humans, but all that matters about the radiation is how close you are to it and how long you're exposed to it. Okay. If you've got a really, really high dose for a really long time, it can kill you. But in a lab, if you're using tweezers and you're a safe distance away and you're not exposed to it for longer than half an hour, you're going to be fine. Okay, so it's all about the time exposed and the amount at which you're exposed to it and the distance that you're away from it. Can cause cancer, yeah. Cool. Okay, so let's talk about the uses of these radiations. They are dangerous. They are dangerous, absolutely. Nobody's debating that, but they do have some useful uses. So irradiation is just the act of radiating something. So the act of alpha, beta, or gamma hitting something. And irradiation can be used to preserve fruit sold in supermarkets by exposing the fruit to cobalt-60. And when we do that, it kills off all the bacteria and it preserves that fruit in the supermarket. We can also use it for sterilization. So we can use gamma for the sterilization of surgical instruments. If we blast some medical tweezers with gamma, that's going to kill off all the bacteria. And a really cool use for it is water supplies can sometimes be contaminated with radioactive isotopes. And we can actually use that to find leaks in pipes. So when there's a buildup of gamma emissions in a certain area, we take our Geiger-Müller tube and we find that there's a really big buildup of gamma emissions, which could mean that contaminated water is being leaked out. So by detecting where we've got a lot of gamma emissions, we can find where there might be a leak of contaminated water. Okay, these are two specific uses that you need to know in depth. So the first one is smoke alarms. Smoke alarms, the smoke alarm in your house has a radioactive substance in it. That radioactive substance emits alpha. Okay, that radioactive substance is an alpha emitter. Alpha, as we know, ionizes the air. Okay, it ionizes, has a very high ionizing power, which basically means that it knocks out electrons from the air and it charges up that air. That air is in a gap in the circuit. And by the alpha ionizing that air, it can create a current. Okay. In a fire, smoke would absorb those ions. Smoke would absorb all of those charged particles. And that would break the circuit, which would sound the alarm. Okay, so it's all to do with the power that alpha has in ionizing that creates this charge, that creates this connection in the circuit. But if smoke is detected, smoke absorbs all of these ions, all the work that alpha's done to ionize, and breaks the circuit. Okay, so smoke alarms use the ionizing power of alpha. Okay, other uses. Another use that you need to know for beta is metal foil production. So in foil factories, they have a radioactive source which sends out beta. So it's a beta source here, the foil is here, and then there's detectors underneath. Okay, the radioactive source is constantly emitting beta. That beta may or may not get through the foil. If the foil is too thick, the beta will obviously not be able to get through. If the foil is too thin, too much beta gets through. Okay, so the detector measures the amount of beta that gets through the foil. If it's too thick, there's not going to be enough beta that gets through, and the detector will sound alarm and say, your foil is too thick, too much beta got through. Okay, and that is all because of beta being able to go through certain thicknesses of foil. Okay. Gamma isn't used because it would just pass through unaffected, and it wouldn't be sensitive enough to detect thicknesses. And alpha isn't used because it would just be blocked by the foil. It just simply wouldn't get through. Hopefully that makes sense. The more beta that gets through the foil, the thinner the foil is. If less beta gets through, the thicker the foil is. Either way, the foil is not the right thickness, yeah? So the factory has a certain thickness that they need the foil to be, and if it's too thin or too thick, the beta source and the beta detector can detect that and sound an alarm and tell the rollers to roll it out a bit more. So again, another really cool use of radioactive decay that isn't to do with medicine and isn't harmful. Okay, so we've already talked about activity, and I just want to reiterate the point that activity is the number of decays per second. Okay, activity is the number of decays per second. Very, very similar to count rate, which is also the number of decays per second, but it's the ones that the Geiger-Miller tube picks up. So it's the number of counts that happen every second. So how much does that digital display go up every second on the Geiger-Miller tube? That activity is the number of decays that happen per second. So we already said that the unit of activity is the becquerel. 1 becquerel is equal to 1 decay per second. So if we have a higher number of becquerels, we have a higher amount of activity. As the nucleus begins to decay, that activity drops and drops and drops. It's not ever possible to say when a radioactive substance will decay, but we can say how many we think will decay in a certain amount of time. Okay, this is all to do with the really random nature of radioactive sources. Okay, count rate. Count rate is the number of counts recorded each second by a detector. Maybe that's the Geiger-Miller tube. Okay, so how much is your digital display going up by every second? Just check my questions. Okay, cool. Half-life. Half-life is this idea of the time that it takes for half of the unstable nuclei in a sample to decay, or the activity of the sample to half, or the count rate to half. It is not half the lifetime because we don't know. Okay, it is how long it takes to get half of the unstable nuclei, or half the count rate, or half the activity. So this graph here is showing count rate against time. The half-life is that point at which the count rate is halved. So if it starts with a count rate of 600 counts every minute, what is it at 300 counts per minute? How long has it taken to go from 600 counts per minute to 300 counts per minute? What do we think? Put answers in the chat. What is the half-life of this specific substance? How long did it take to go from 600 to 300, or maybe you pick 300 to 150, or maybe you pick 150 to 75. It doesn't matter. It's just how long does it take for the count rate to half? How can we detect that from our graph? Maybe we draw a horizontal line to the graph. What do we think? What is the half-life? Okay, lots of you saying 45, some of you saying 50. Correct answer is actually 45. So we need to look at one number and see when that number is halved, how much time has elapsed. So it starts off at 600 minutes, counts per minute. When we halve the count rate, we get 300 counts per minute. We need to decide how long does it take from the substance to go from 600 counts per minute to 300 counts per minute, and that's 45 minutes. They've actually put it on the graph for you already, but it's about you interpreting that after it's halved, it's 45 minutes. It is not 75 minutes, okay? It's not just half the time. That's not what half-life is. Half-life is the time at which the count rate is halved. So the time that it takes for the count rate to halve, or the activity to halve, or for half of the unstable nuclei to decay. Okay, now this is higher tier stuff, but there is an equation that is associated with half-life, and I want to show it to you guys. So a particular radioactive isotope has a half-life of 6 hours. So as always, let's go in and let's highlight the important information. So half-life of 6 hours. A sample of this isotope contains 60,000 radioactive nuclei. Okay, so it starts off with 60,000 nuclei when it's really, really radioactive. And it has a half-life of 6 hours. That means that after 6 hours, that number, 60,000, will halve and go to 30,000. So it takes 6 hours for the number of radioactive nuclei to halve. We have to calculate the number that will be left after 24 hours. So we already know how many will be left after 6 hours. That's 30,000, right? It just halves. But what about after 24 hours? Well, that means that we need to use this equation here. So this equation is the count rate after n half-lives. So what is the count rate after n half-lives? And that is equal to the initial count rate divided by 2 to the power of the number of half-lives. Probably the most complicated equation in the physics GCSE because it has this weird format here, 2 to the power of n. Okay, don't let that freak you out. N is just a number. It's just the number of half-lives that have elapsed. And we do 2 to the power of it. Okay, so we are working with 24 hours. So how many half-lives is that? How many half-lives is 24 hours? If one half-life is 6 hours, how many half-lives is 24 hours? That's our first step. Work out n, the number of half-lives that have been elapsed. The number of half-lives that have been elapsed. Okay, so let's write this out. If one half-life is 6 hours, then how many half-lives is 24 hours? Hopefully you can see that that would just be 4. We times the right side by 4, we times the left side by 4. If one half-life is 6 hours, then 4 half-lives is 24 hours. So what that's basically telling us is that after 24 hours, our radioactive isotope will have halved its number of nuclei 4 times. Okay, so it will have halved, 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 and halved again. And we need to work out the number after it's done those 4 halves. Okay, and the way that we do that is with this equation. So we want to work out the count rate, the number of unstable nuclei after n half-lives. N in our case is 4, the number of half-lives that have gone. And so we do the initial count rate divided by 2 to the power of the number of half-lives. So what is our initial count rate? What is our initial count rate? Our initial count rate is this here, 60,000. Okay, that's what it starts with. It starts with 60,000 unstable nuclei. We already know that N is 4. We've elapsed 4 half-lives after 24 hours. So when we plug that into our calculators, what do we get? 60,000 divided by 2 to the power of 4. What is 60,000 divided by 2 to the power of 4? I make it 3,750. Yeah, cool. Lots of you are saying 3,750. That's absolutely correct. So our count rate after 4 half-lives is 3,750. Can anybody tell me what the count rate would be after 2 half-lives? We've just done it with 4. What would it be after 2 half-lives? Does anybody know? Let's have a look. What are people saying? 60,000 divided by 2 to the power of 2 is hopefully what you've put into your calculator, which is just 15,000. Good, lots of you got that right. Well done. So 15,000 after 2 half-lives and 3,750 after 4 half-lives. Perfect. So quite a scary looking equation, but actually when we break it down, all we need to know is how many half-lives have elapsed. Okay, so you'll always be told how long half-life is, and then you'll be given another time. And with that time, you need to work out how many half-lives that time is. Okay, half-lives and instability. Isotopes with really short half-lives have the most unstable nuclei, which means that they lose a lot of radiation quickly. As activity decreases, the rate it gives out radiation decreases. And we can see that with this graph here. So as time goes on, the curve starts to flatten. Can you see that it's really steep here? But after 125 minutes, it's actually really shallow, which means that the count rate's actually not decreasing by much. It loses a lot of radiation here, but that rate starts to decrease and our curve becomes shallower and shallower. Okay, we've got another half-life question. Really want to drill this down. So what is the half-life of a sample where the activity drops from 1,200 down to 300 in 10 days? What is the half-life of that sample? Let's have a look. What are people saying? Lots of you saying 5 days. Perfect. That's the correct answer. What you might have done is seen that 1,200 to 300 is halving twice. So you half it once and you get 600, and then you half it again and you would obviously get 300. Okay. So if it's been halved twice, that's 2 half-lives. And if 2 half-lives is 10 days, then 1 half-life is 5 days. They will give you that equation in the exam, by the way, guys. Yeah, I don't know. I'm just trying to write that out. Let's get rid of that. So 2 half-lives is 10 days, then 1 half-life is 5 days. Great, that's really, really good. Hopefully that equation's making sense. If it is, that's brilliant. That's higher tier stuff. That's the top stuff that you do in year 11. So if you're getting it already, you're ahead of the curve. Really well done. And that includes A-level maths in that equation. So again, really well done if you got it. Cool. Nuclear fission. Nuclear fission and nuclear fusion is the last 2 parts of this topic. So we're nearly at the end. Nuclear fission and nuclear fusion, what's the difference between them? Can anybody tell me what the difference is between fission and fusion? They sound really similar, really easy to get confused. What's the difference? Okay, lots of good answers. Fission is the splitting of nuclei. Good. Fusion is when they're joined. Brilliant. One splits, one joins, splitting and joining. Fusion turns smaller elements into heavier ones. Brilliant. One splits atoms and the other makes them collide. Yeah. Yeah, you're all absolutely correct. So nuclear fission is splitting them up. Fusion is joining them together. So nuclear fission is much more common. It's much, much more easy to do. So how does it work? We need to look at the diagram and I'm going to try and explain it to you. So we have a unstable nuclei. In this example, our unstable nuclei is uranium-235. Okay, that's our unstable nuclei. That's just one isotope. It could be anything. That unstable nucleus absorbs a neutron, just a random neutron, and it absorbs it. When that happens, it gets split into 2 daughter, if you like, nuclei, into 2 smaller nuclei. Still unstable, but just 2 smaller, equal-sized nuclei. Okay, so the neutron is absorbed and it gets split into 2 nuclei. Those nuclei are released, but also at the same time, some more neutrons are released, some gamma is released, and some energy is released. Okay, they're all fission products. So not only do we get these 2 smaller nuclei, we also get gamma, and we get energy, and we get some more neutrons being spit out. Okay, so the neutrons that get spit out because of this splitting down can also go on to be absorbed by more uranium-235, and the process happens again with those released neutrons, and we get a chain reaction. So that process can keep happening so long as neutrons keep getting emitted. Does anybody have any questions about that process? Let's have a look. Will it always be uranium? Good question. Yes, uranium-235 is always used by AQA because it's nice, right? They don't want to trick you out. It's always used by AQA. It's the most common anyway. It's the one that we actually do use in real life. And it will mostly always be uranium-235. Can you use a control rod to control it? Yes. So this process is done in a nuclear reactor. It has to be controlled. If it's not controlled, then it's basically a nuclear bomb, which obviously we don't want. So this process needs to be done in a nuclear reactor in a nice controlled environment in order to be safe. Okay, so fissionable isotopes, it has to be a fissionable isotope. The most common are uranium-235 and uranium-238. Okay, if this nuclei is just anything, fission might not happen. Has to be uranium-235 or uranium-238. In your exams, though, it will most likely be uranium-235. Okay, fusion. Fusion is less common because it takes so much energy to happen. It takes so much energy to bring two nuclei together. But it does happen in stars. So stars release energy by fusing two hydrogen atoms into helium. When that happens, they release energy. But it only happens if these elements are heavy enough. Yeah, they're heavy enough and they have to be the right mass. And that's really the only instance of fusion that you have to know about is in the sun. So in the sun, the sun is constantly fusing hydrogen, it's constantly fusing it to create helium and keep burning and keep releasing energy. If the sun were ever to stop doing that, then we basically wouldn't have a sun. So this fusion process keeps happening and it keeps fusing hydrogen and it keeps releasing thermal energy. But it can only happen if the elements that are being fused are no heavier than an iron element. Okay, they're not, they're hydrogen, but fusion can only happen if we have elements that are lighter than iron. Okay, iron, the element. Okay, right, that brings us to the end of the content. So we've got a nice amount of time to go through some questions. And I actually want to start with an electricity question because obviously we did that first and it's, you probably are going to remember it the least, so let's go over it. The equation which links current, potential difference and resistance is potential difference equals current times resistance, otherwise known as V equals IR, otherwise known as Ohm's law. The question asks us to calculate the potential difference across the battery in the circuit. We're already given the current and we're already given the resistance of each resistor. And we want to know the total potential difference in the circuit. So V equals IR, but we're trying to work out V, so we don't need to rearrange the equation, which is good. But we do need to fill in a value for I and a value for R. So what is the value for I and what is my value for R? What do we think? Put your answers in the chat. What is my value for I and what is my value for R? Good. I is 0.4. Brilliant. Lots of you getting that. But what is R? R is tricky. We have to do a little mini step to get R. And that many steps is adding the two resistances first. Okay, so it's not correct to just do it with one resistor. We have to add them first and then use the total resistance in the circuit in our equation. We have to remember the fact that resistors in series add. Okay, so V equals 0.4 times 30. Well done if you got that. And what is 0.4 times 30? Give you a few seconds to put it into your calculator. That would be 12 volts. Okay, so the total potential difference across the battery is a 12 volt battery. So where you could be tricked out there is by not adding the resistances first. Okay, so you've got to add those resistances first, otherwise you're going to get the wrong answer. Okay, next question. Some substances are radioactive, as we know, and that's because they're unstable. and they may emit alpha or beta particles in order to become more stable. This question is a wordy question, and it asks you to describe the characteristics of alpha and beta, not gamma, in terms of their structure, penetration through air and other materials, and their deflection in an electric field. Okay, so let's talk about this one. This is a 4-mark question. You've got to do 2 different particles, and you've got to talk about 3 different things for 4 marks. So first of all, these kind of questions are really nice, right? Because they lay out exactly what they want you to write. Structure, penetration, deflection. Don't write anything else. Don't write anything more. It's really nice. Just go bullet point by bullet point and answer it. So structure of alpha. What is the structure of alpha? We already know that it's a helium nucleus. Okay, absolutely fine for you to also write 2 protons and 2 neutrons. Structure of beta is an electron. Okay, fine for you to say that. It's not asking you what beta decay is, it's just asking you what the structure of beta particles is, which is just an electron. Penetration through air. Penetration through air. So alpha penetrates through air with less than 5 centimeter range. Beta penetrates through air with 1 meter. Deflection in an electric field. Okay, deflection in an electric field is a weird one. What that means is if you were to put the particle in an electric field, would it repel or would it attract? Well, an alpha nucleus is positive. Okay, so it would be deflected in an electric field. An electron is, again, obviously negative. So again, it would be deflected in an electric field, and you can write that. Cool. Next question. Let's do an electromagnetism one. Okay. Diagram below shows a transformer, which we briefly discussed yesterday. And the transformer, just to remind you, is a rectangular magnet, iron magnet, with coils on one side and coils on the other. And the number of coils on each side will tell you whether it's a step up or a step down, and therefore whether it's going to increase the voltage or decrease the voltage. So in this question, we have 2 coils, primary coil and our secondary coil, and they have, as you can see in the diagram, 2 different amounts of turns. The primary coil has 48,000 turns and the secondary coil has 4,000 turns. If the input voltage is 240, calculate the output voltage. Okay, so let's think back to our equation. Our equation is the primary amount of coils divided by the secondary amount of coils divided by the secondary amount of coils, and that is equal to the primary voltage, or the input voltage, divided by the output voltage. Okay, cool. So our primary coils is 48,000 and our secondary coils is 4,000. So we're going to work out the left-hand side of the equation first. Let's work out that fraction. So what is the ratio of the number of coils, primary to secondary? Work that out, put it in your calculator. What is 48,000 divided by 4,000? What do we think? So 48,000 divided by 4,000 is 12. So that's our left side of the fraction done, our left side of the equation done. Now we need to make the right side of the equation also equal that. So that means that input voltage divided by output voltage should also be 12. Okay, and if the input voltage is 240, what does that mean the output voltage is? So what do we need to divide 240 by to get 12? Cool, so hopefully you got 20 volts. So our output voltage is 20 volts. Cool, and because we have a smaller output voltage than our input voltage, that makes this a what type of transformer? A step up or a step down? So a step up or a step down. If the voltage is going from a higher to a lower value, it is a step down transformer. We're downing the voltage. How could our transformer be adapted to make it into a step up transformer? What could we do? What could we do to make this into a step up transformer, not a step down? Good, exactly. Lots of you getting it right. Put more secondary than primary coils. Good. Okay, let's have a go at another radioactive decay one. So this graph shows how the count rate from a sample of uranium-238 changes with time. So on the y-axis, you've got count rate in counts per second and time in millions of years. This is really, really slowly decaying radioactive substance. The graph can be used to find the half-life. The half-life, we know, they're telling us, is 4,500 years. But how would you use the graph to know that? What would you do? What would you guys do? How would you work out the half-life from this graph? You've got an initial amount of an initial nuclei, an initial count rate. And remember, the half-life is when that count rate is halved. What would you guys do? So what I would do is I would put a line after it's halved. So it's 1,000 at the beginning, and after it's halved, well, that would be 500. Yeah, that would be 500 after it's halved. Let me make that big so you can see. And then I would draw a line down from the graph to work out at what point it hit the x-axis. And I can see that that would be 4,500. Okay, so remember, it is not half of the time. It's not half of its life. That is not what half-life is. I know it's confusing, but half-life is the time taken for the count rate to half. So if the count rate started at 1,000, how long does it take for it to get to 500? So we draw a line from 500 and we draw a line down, and we can work out that it takes 4,500 million years. Okay, 3 multiple choice questions here on electromagnetic induction. Can we have a go at answering in the chat? You can call this A, B, and then C. What do we think? What is another name for electromagnetic induction? How can the direction of an induced potential be reversed? And how is contact between the coil and circuit maintained in an alternator? So just write A, B, or C. Cool. So another name for electromagnetic induction is the generator effect. It generates potential difference. That's how you can remember it. How can the direction of an induced potential be reversed? By changing the direction of the magnetic field. And how is contact between the coil and circuit maintained in an alternator? So that's an AC generator. Alternator is an AC generator. So that is slip rings and brushes. Okay, I think we might have time for maybe one more question. Let's try this one. So, a set of decorative lights is made from 9 identical lamps connected in series. Each lamp is designed to take a current of 0.5 amps. The set plugs directly into the 230 volt mains electric supply. So we already know that voltage is 230 volts and current is 0.5 amps because current is the same everywhere in series. So it doesn't matter if each lamp takes 0.5 amps. Every lamp takes 0.5 amps and that's the same everywhere. So that is the total current in the circuit. Current is not shared in series. Cool. So we already have V and we already have I. So you may already be thinking that we can divide them to get R. If V equals IR, then R equals V over I, in which case we have R equals 460 ohms. Because we're doing 230 divided by 0.5. And then that's the total resistance of all of our 9 lamps. So the resistance of one lamp is 460 divided by 9. So the answer to the first part is the resistance of one of the lamps, which is 460 ohms divided by 9. But the total resistance is 460 ohms. Okay, guys, that brings us to the end of the session. I really hope that you enjoyed all 3 webinars this week, and I hope that you learned lots. Remember, they are recorded and you can go back and you can try those questions anytime. I really hope you've enjoyed the sessions and have a lovely Christmas and a new year. Thank you all for listening.